speakers, esteemed participants, ladies and gentlemen. My name is Kalpana Adhikari from Committee for International Commission on Large Dam India INCOLD. On behalf of INCOLD, we extend a hearty welcome to the dignitaries and resource speaker, including ICOL President, Mr. Michael Roger, Vice President ICOL Committee on Concrete Dam, Dr. Quentin Shah, Dr. Malcolm Dustin, longest serving member on the ICOL Committee on Concrete Dams and chairman of the committee that drafted ICOL Bulletin 109, co-founder of ICOL's Young Engineers Forum, Dr. Marco Corran, and other world-renowned experts, Mr. Francisco Ortega, Mr. Christopher Hicks, Mr. Rafael, Mr. Tim Dolan. I also welcome ICOL Vice President and President INCOL, Mr. Devendra Kumar Sharma. Kindly excuse if we missed name of some of eminent ICOL family members. We hope yesterday you have very educative and informative session and would have ignited your mind to know more details about the RCC technology, which is the need of the hour. Ladies and gentlemen, now we have today's first resource speaker, Mr. Michael Roger, ICOL President, who would be making presentation on RCC dam rehabilitation and raising. Let me introduce briefly about this speaker.
Kalpana.
Mr. Michael Roger is the Principal Civil Engineer and Senior Project Manager at Stantec Consulting Services. He serves as Stantec's Global Practice Leader for dams with responsibility for corporate management and quality in the dam practice of dam engineering. His experience includes technical and management participation for more than 200 dam projects worldwide, including dam safety, design, and construction. His experience includes management of multidisciplinary team for design of dam and cofferdams with construction, including technical scope direction, senior technical review, consulting review board roles, and project control oversight. He is a recognized technical expert in the field of dam safety engineering at the domestic and international level, with the specialty in roller compacted concrete RCC structure. Mr. Rogers currently serves as President of the International Commission on Large Dam, ICOL. Previously, he served as ICOL Vice President and Chairman of the Technical Committee on Concrete Dams. He also served as President of the United States Society on Dams and Chairman of the USSD Technical Committee on Concrete Dams. He is also a past member of ASCE's Hydraulic Structures Committee, including the term as Chairman. Mr. Rogers has contributed to documentations of the state of practice through his professional engagement in USSD, ASDSO, and ICOL for more than 30 years. He has contributed to more than 50 technical papers and technical articles for professional magazines. As chair of the USSD and ICOL Technical Committee of Concrete Dams, he contributed to several technical white papers and ICOL Bulletin, including the recent ICOL Bulletin 177 on concrete compacted roller compacted concrete dam. May I request our President, ICOL President and ICOL Vice President and ICOL President, Mr. Devendra Kumar Sharma, to say a few words about this program. TK sir?
Yes. Yeah, sure. Hey, just a minute. ICOL President, Mr. Michael Rogers, Mr. A.K. Dinkar, Secretary General INCOLD, Francisco Ortega, Resource Speaker for today, along with Mr. Michael Rogers, delegates from all parts of India, ladies and gentlemen. Just now, Kalpana has given you a brief introduction about Mr. Michael Rogers. So on behalf of the Committee of International Commission on Large Dams, India, which is known as INCOLD, and the International Commission on Large Dams, ICOLD, it's my proud privilege to welcome you all to second day of this virtual workshop on applicability and feasibility of roller compacted concrete dams, which is being held for 3 days. It was yesterday, today, and tomorrow on 12th of November to 2021. Kalpana has given you introduction about Mr. Michael Rogers. Michael Rogers, whatever introduction is given about him, that is small because Mr. Rogers is well-read personality, very well, most knowledgeable, and he's one of the most effective presidents of ICOLD, what I've seen so far. Mr. Michael Rogers has steered ICOLD in the right direction, and he has given such a big thrust, and the meetings of High Court which have been conducted, I think during his tenure, maximum number of High Court board meetings would have been conducted. So Mr. Michael Rogers will talk to you today about rehabilitation and raising of Cross Dam in Denver, Colorado. Let me share with you the type of work they have been doing, and the engineering part of it. They have been working on it for I think last 7-8 years, or rather there was a report prepared in the beginning that they will augment by construct another dam. Then while it was being approved, it was considered that they will carry out raising of the existing dam, and it would be very interesting to learn from him that how raising of an existing dam is being carried out, and even in that case RCC is being used. In the afternoon session, we will have Mr. Francisco Ortega. He will talk about materials and mix proportioning. We are lucky that both the speakers, who are world-renowned authorities in their own field, have agreed to our request to deliver lecture during this workshop. So with these small words, I hand it over to my friend, Mr. Michael Rogers, President, ICOLD. Thank you. Mr. Rogers, your field now.
Well, hello, everyone. It's very good to be here with you for this training session. I have sent the presentation recorded with my background, and so if the presenters or the technical people are ready, go ahead and start the PowerPoint show.
Sure, sir. May I request my colleague to play the recorded presentation received from Mr. Michael Roger?
I will stay on and be here after for questions. Thank you.
Sure, sir.
Sure, sir.
Hello, my friends in India. It's good to be with you again. I'm sorry I'm not there in person, but perhaps we will get together soon. Certainly at the ICOL 2022 Congress in Marseille. I hope to see many of you there, and certainly ICOL 2024 in New Delhi. I plan to be there and visit with you in person. But for today, this is part of the RCC virtual workshop, and I'm going to be presenting to you today on RCC dam rehabilitation and dam raises. And so I hope you enjoy that. I'm going to turn my video off now to save a little bit of space, and then we will proceed. Before we begin to talk about RCC, let's talk about safety. And I have a safety minute here, and it has to do with anytime you get out to a site and you put your personal protective gear on and you walk into the construction area. So what do? The first thing you should do is stop, look around, and see what critical risks you see, what safety risks you see. Where are the energy hazards? Energy are these things: gravity, mechanical energy, electrical energy, chemical energy. These are the the energy wheel items that can cause some safety issues for you. So look at this picture and see, where do you see them? Where do you see the hazards? What safety issues could occur while you're out on the site, and how can they be prevented? So some of the quick things here are, we have a mobile equipment device here. And so it could have some energy moving back and forth, up and down. There's some gravity energy here on dropped objects from the boom that's above. There's some stored energy here, the water behind the radial gate. Um, the heat is an energy source. Heat being out in the field, also ultraviolet radiation. There's a lot of water here, and so slips, trips, and falls are very common in these areas, so be very careful. Just being outdoors, there are bites and stings that can happen, so we want to be careful with that. You can see posture here, bending over. Um, so we want to be careful with that to not hurt our bodies. And then also the water hazards generally around the site here. So that's just a quick safety moment. And when we take a minute to be safe, then everyone goes home safe. So let's begin with roller compacted concrete and using RCC in dam construction. This presentation today will be part of ICOLD Bulletin 177, which I was part author of, and that includes other uses of RCC, uh, stuff that may just be a little bit out of the ordinary. And so I'm going to talk about these topics today, from overtopping all the way through raising of concrete dams. These are primarily rehabilitation aspects of dams, but they can be used for new dams. And then I will present some case histories from the work that I've done and have been fortunate to be involved in. Okay, so let's begin at the beginning. And Chapter 8.1 is just a general introduction to RCC for rehabilitation and dam raises. We know from the previous lessons and the previous chapters of the bulletin that RCC is a very adaptable approach to construction for concrete dams and appurtenant structures. This is based on site locations. Different sites have different adaptabilities to RCC and the success of RCC. And the RCC can adapt to these different locations. It can adapt to different functions that we're looking for, whether we're trying to build a new dam or to rehabilitate an existing dam or raise an existing dam. And a lot of that is a function of the material availability. So the materials for the concrete, the rock for the aggregates, the cements, the fly ash, these are all very important considerations as we start to think about an RCC dam. We know that RCC offers the advantages for construction based on fast placement, uh, getting a lot of material down and compacted very quickly. And a big part of that is forming, or the lack of forms. We're, as shown in this picture here, we're looking at forms primarily on the upstream and the downstream side to simplify the construction. And that allows us to go fast. And when we go fast, we save money, and we have good economics of construction. So what are we going to talk about for today? At least for this presentation, I'd like you to come away with um, the idea to inspire creative thinking. RCC is one of those materials and methodologies for construction that allow us to be creative. And I have some examples for you today on projects that I've been involved in that have been very interesting in using these materials in creative ways. And a big part of the economics and the creativity is to keep it safe and keep it simple. The KISS process. We want everything to be safe, and we want people to go, all of our friends and coworkers to go home safe at the end of the day to their families. And the success of RCC has been found time and time again is the simplicity of the design, the simplicity of the construction. Keeping it simple allows us to go fast and allows us to get good quality and allows a project to be successful. So favorable RCC property include minimal forming requirements. We've talked about generally using these forms on the upstream and the downstream sides of dams. The sturdy material properties, it's concrete that we're putting down, and so it has a strong resistance to erosion under high velocity flows, which is good for our hydraulic structures, our spillways and our stilling basins, our erosion protection uses of RCC for dam rehabilitation. An economic project cost will be based on a relatively low manpower requirements. Getting the materials placed quickly with a minimal amount of materials and manpower will lead to economic project costs. And we want to try to minimize the amount of manpower by keeping it simple and keeping it to the basics of roller compacted concrete. Also being flexible to the varying site conditions. As the site conditions change day to day, week to week, we need the materials to be adaptable to the structures and to the environment that we're working on. We want to have the materials readily available from conventional concrete source plants and from the area, the cements and the fly ashes and the rocks for the aggregates and the sand for the concrete. And so these are very important to have these materials readily available from local sources. As we look at rehabilitation, we take a step back and we look at where did this begin? At least for me, this started in the mid 1980s when engineers started looking at roller compacted concrete as a methodology and approach for dam rehabilitation. And my early career was all about dam rehabilitation. And one of the first topics or applications of RCC that I was involved in is overtopping protection. And this is showing you a typical cross section of RCC overtopping protection. There's a lot of papers out there on this type of approach. It's been around for more than 40 years. It's very simple, but elegant and creative. It allows us to use existing embankments as overtopping spillways with the protection that RCC provides for the dam to keep the dam stable and to keep from losing the entire dam due to erosion. But there are certain key aspects of this engineering that we have to watch for. We need to have an upstream cutoff wall to prevent undermining and erosion in the upstream side. We need to have a hydraulic control over the top of the dam, a good thickness that is stable and strong, an under drainage system with a good filtered drain, and an apron with a downstream cutoff wall, again, to prevent undermining and erosion under high velocity flows. The RCC as an overtopping protection allows the dam itself to be used as an auxiliary emergency spillway. So this is a cool, very nice application of RCC. It's a very simple approach to using the material to create an auxiliary or an emergency spillway on part of the dam. And what we do is we have to be careful that we protect the dam under construction conditions. And when we're done, if the project is right, the RCC can even be covered for minimal environmental impact. This project shows that there was a thin layer of soil and grass seeded over the top of the RCC. So when it was finished, it looked very much like before the rehabilitation happened. But should an overtopping event happen, the overtopping water will very quickly wash out the overlying soil and grass and it'll open up the emergency spillway for RCC. We know that RCC is adaptable as a hydraulic structure along the crest, and that crest can be modified depending on the local conditions for a broad crested weir. Even a sharp crested weir or an OG weir control can be added there. And most of the time, we don't want to have any type of gates controlling on these emergency spillways. We want them to operate without manual intervention. So some of the critical design features that I mentioned were the erosion protection at the upstream and the downstream side to prevent scouring and undermining that could lead to the destabilization of the RCC. An under drainage system that collects water, prevents hydraulic uplift, and provides filtered exits. And then a hydraulic control at the crest with no gates. And the best projects that I've seen have all been a broad crested weir, a simple broad crested weir control that allows the project to function as an emergency spillway. Important design features are included here, and we've talked about the drainage and the drainage beneath the terminal structure, then the upstream and the downstream cutoff walls. Okay, so let's look at a case study. So this is an older picture of overtopping protection on an embankment dam using RCC. In this case, the hydraulic control was an OG type of weir control, and you can see the RCC on the downstream side and along the abutments that provides protection of the soft soils and the erodible surfaces that would be exposed under overtopping conditions. And from the size of the people on here, you can get a sense of the scale of the structure. This picture also shows the potential erosion areas that RCC has been put in to protect down at the Stilling Basin and at the upstream, and there's a cutoff wall underneath this weir that prevents erosion or scour from the upstream side. The steps themselves offer some energy dissipating function as well as the Stilling Basin on the downstream side. And finally, the ungated approach for the hydraulic structure. This is a simple, nice approach, an elegant approach where manual control during a flood is not necessary, and overtopping happens over the ungated crest of the spillway. Let's move on to the next topic, which is dam stabilization. And I've had the fortune to have a couple of these different projects. And by stabilization, I mean structurally upgrading a concrete or a masonry dam for either static or dynamic loading cases. We can use this approach for many of our older structures that perhaps the design criteria have changed for either static or dynamic cases. And the structures themselves are still in good shape, but need some additional stabilization, some additional mass to stabilize the structure. And RCC has been used successfully to stabilize existing concrete dams, but by providing this additional mass, primarily at the downstream side of the existing dam, because that's an easy, accessible place, or in the case of multiple buttress type dam, multiple arch dams, infilling between these buttresses. So the protection of the downstream face by putting RCC against the downstream face, in addition to providing structural upgrades, can also improve the freeze-thaw resistance of the existing structure by providing a thicker concrete on the downstream face. The rehabilitation itself increases the life expectancy and generally improves the aesthetic appearance of the structure by providing a newer appearance. So there's some different approaches for the stability. One of the projects I was involved in used the buttress approach, and that's shown in this picture here, where the existing older dam needed some additional stability. And so RCC was placed on the downstream side of the existing dam against the structure and provided additional mass on the downstream side and improved the stability to meet the static and the dynamic situation. Infilling between these hollow buttress type dams is also a possibility. This is an interesting case study in California. This is an Eastwood type of dam, a multiple barrel arch dam that I worked on for that had dynamic stability problems, earthquake stability problems. And so this is the area between these buttresses, a close-up view, as a base layer of conventional concrete was being placed before the RCC to smooth out and level out the bottom of the buttress. But you can see how the concrete is starting to come up. The concrete is not going to go all the way to the upstream arch, but it will be in the middle here and enough to provide some stability. This is further in construction. You can see the concrete, the RCC starting to come up. And then this is a picture of the completed structure. Um, and we designed this to leave the appearance of the multiple buttresses on the downstream side. We put in just enough infilling of concrete to stabilize the dam, but we left the general appearance to keep the character of the dam intact. These buttresses are hollow and they include the outlet works as part of the dam. Moving on to chapter 8.4. Now this is the erosion protection part of RCC, where we use RCC for protecting areas subject to aggressive flowing of water. And these are areas like spillway chutes or channel linings, stilling basins, spillway aprons, even upstream freeboard, wave protection. There are barrier separation dikes and plunge pool shaping. It's been used in plunge pools that have erosion problems to provide additional erosion resistance. And some key design considerations for the RCC in this application or for these type of projects is the durability. You want to be looking at a mixed design or an application that provides good erosion resistance to high velocity flows, and look toward the long performance of the materials. In some cases, the energy dissipation is going to be important, or a deflection or a reflection of the water away from structures. And so that part can sometimes create some energy concerns, and we want to be sure that we don't cause any distress to the structure. And finally, in channels or even spillways, hydraulic roughness can sometimes be a consideration, the Manning's N. And I just bring this up to recognize that RCC can have a different Manning's N roughness than conventionally vibrated concrete. So let's look at an example. And Platter Nervasi Dam in Greece is a good example of this, provided by Malcolm Dunstan and Associates. This is a 95-meter high, 305-meter long RCC dam. And the structure itself is a good application and a good project for RCC. But what I wanted to show in this example here is the downstream training wall, this channel wall that was developed using RCC to prevent scour and erosion along this wall as the spillway is operated under high velocity flows. And so the designers here were using the RCC for both the dam and also the downstream wall. And I've seen that approach also used on upstream walls. In some cases where there's a high velocity flow or there's unstable walls of the valley upstream of the dam, RCC can be used as a slope protection to stabilize those slopes. And then there's general slope protection for erosion. And I'm going to talk about the case study of Oroville Dam that I was involved in. And this is the emergency or the auxiliary spillway portion. And in the spillway, in the picture here, you can see on the left side the weir of the auxiliary spillway and the erosion that happened after this spillway was used for the very first time. The project was more than 50 years old, had never used this auxiliary spillway. And the first time it was used, it created a high degree of erosion, and this large eroding area near the bottom of the weir was a head cutting situation moving upstream and caused considerable concern and eventual evacuation of more than 200,000 people because it appeared to be endangering the stability of the dam. So uh, as an engineer involved in this, we came up with a solution using RCC that put RCC over this entire area downstream of the weir and created a splash apron for protection. And I want to tell you a little bit about that design and what went into that. And so this is schematic showing what we were facing. A portion of the emergency spillway had a weir that controlled it from varying heights, from about 2 meters to about 8 meters high, and on the different sides. And so it was a varying height across there. And then the area uh, further to the right abutment, where the flatter area is, had no control. And this was just a flat overtopping of the parking lot area that came into the same area. And so as engineers, we looked to put a splash pad of RCC over the entire area. And you can see the approach on the design approach in the lower left-hand corner here, the emergency spillway weir. We used RCC as a buttress, as I mentioned earlier. The weir itself had stability issues, and so the buttress provided some increased stability. And then the splash pad itself connecting to a downstream cutoff wall. So some of the basic principles of RCC that we use for an embankment dam protection, the thickness of the RCC and the cutoff wall on the downstream side to prevent undermining, are still applicable and used here. So the splash pad was used for the slope protection and the pad all the way down, and it was stepped to allow energy dissipation as part of its function. And then the downstream cutoff wall that is designed to prevent backcutting and undermining and tying into the deep rock foundation underneath the structure. There are also sidewalls built of RCC to channelize the flows and to keep the flows on the splash pad and moving downstream away from the structure. So this is a simple cross section showing the upstream weir area, and there was an upstream cutoff wall, again using the same principles as we had for embankment dam overtoppings. The horizontally placed RCC to give us a minimal thickness of about 3 meters, and then the downstream secant pile wall that was buried deep into the rock to create a good solid downstream cutoff to prevent any erosion that might happen here in these unprotected areas downstream of the RCC apron, would not allow it to move upstream and endanger the structure itself as it happened in the original event, a flooding event. So this is some construction photos showing the secant pile wall for the downstream toe protection. Uh, this is after the secant piles have been installed and then excavated. So what we're looking here is the RCC pad is going to be on the left side here, and then downstream on the right. And so here you can see a little bit more of this. Now the secant pile wall has been upgraded, and a grade beam has been put over the top of those piles. RCC has been put on the downstream side of the wall to create some additional protection for undermining. And now we're just starting to build the RCC horizontal lifts of the splash pad moving upstream. So we're starting from the lowest point here, and this is going to be the lowest point here, and we're moving upstream in 2 RCC lifts, and these are two 30-centimeter lifts moving upstream. And this slope, this one-to-one slope, is an unformed slope, and the contractor was able to get compaction along that slope using a special machine that had a vibrating plate on it to create that slope. So this next slide then shows continuing work, and you can see these steps now being formed moving up the slope, and these are all done in horizontal lifts like we normally see an RCC dam being built or an embankment protection, but we're using our imagination here to create this big splash pad and almost a stilling basin area using RCC. And we're being able to do it very quickly because we don't have forms. This one-to-one slope that we're using this vibrating plate is actually working very well and allowing the contractor to very quickly place RCC and move up the slope. This is an interesting picture, about the same time as the last picture was taken, and it shows the progress. And this is about half of the RCC. This was done in 2 halves, so this is about half of the splash pad. And the wall is just starting to be built on the left side. But as it's moving up, you can see it's protecting the brown area, which is compacted. Uh, it was probably moderately weathered rock, and so it was friable and highly erodible. And then up at the top, the grayer rock, that was more fresh to slightly weathered rock. So that was mostly non-erodible rock. There were some holes in it that the wider areas are consolidation concrete that was put in there, and the RCC is just moving up the slope to fill. And this is near the end, showing the original weir of the structure of the emergency spillway structure. The RCC has come all the way to the top, and you can see by the different angles that have been adapted here that the changing geometry, the RCC allowed us to change the geometry to maintain the thickness, and we still have the steps. The water that's on here is just curing water, but it would prove to be very adaptable. You can see the closer space steps against the weir are the steps of the buttress, and we have the same steps coming all the way to the top. And for this project, we actually used rebar to tie these two structures together. So we drilled and grouted rebar into the existing structure and extended it about 2 meters into the RCC and put a flat plate at the end. And that's how we were able to tie these two structures together with the use of rebar into both structures. So let's move on to using RCC as a foundation replacement. Um, it's especially important that the foundations of hydraulic structures, including dams, are shaped in a proper manner to avoid sharp offsets that could result in stress concentrations. We know this from our basics of creating foundations that are smoothly varying so that we don't have those stress concentrations. And RCC is a good material to create these smoothly varying foundations. And it can be used for RCC dams as well as other type of structures to fill in cavities in the dam foundations and at the downstream toe of spillways. The RCC can be used in the stilling basins for the spillways. It provides a good material, highly resistant to high velocity flows, and can also be used as foundation for dams and other conventional concrete structures, including spillways, powerhouses, and valve houses. I'm going to give you some examples of that in this presentation here. So we go back to one of the early uses of what is come to be known as RCC. And it started as rollcrete at Tarbela Dam back in the 70s. This is documented in the original ICOL Bulletin 126. And so you can look back there and take a look at that. But this was about 900,000 cubic meters of rollcrete that was used after the initial operations of this large spillway started to cause unexpected erosion. And so the RCC was used in the Stilling Basin to create an armored pool, if you will, to resist the erosion, and worked very well. It was a very nice application, one of the initial applications of rolled concrete. This structure this application is a really cool application. This was an RCC dam, Portuguese, down in Puerto Rico, and the dam itself was RCC, but as part of the construction, the engineers designed a foundation for the valve house, and you can see the rock down here at the bottom, and they needed a valve house up higher, and so RCC, an unformed RCC slope, was used with the compacted lifts and brought up a very nice pad to set the valve house for the structure on. A very nice application of RCC for this structure, and it allowed the pipes to be brought through the structure, through the RCC, and into this. And so, and also when these valves operate, there is a good resistance to erosion because of the RCC on the downstream side. And in the background, you can see a very nice, good looking RCC structure itself for the dam. Now, one of the projects that I was involved in as part of my career is the Liebenheim Dam in San Diego. And for this project, this was a high seismic area, and we wanted the dam to be tall in the main valley, as shown in the far areas closer to the right abutment, and then have decreasing height, as it went left and right. Well, that worked fine going to the right, but in the left, you can see we had another small topographic low, an old shear zone, an inactive fault that created a second valley. And since we wanted the dam structure itself to be a certain height across that area, we filled in this topographic low using RCC and created an offset on the downstream and the upstream side using RCC as part of the design, so that the dam itself above this structure in an earthquake reacted as if its height was only the height of the main dam and not as the deeper dam. And so this allowed the dam to perform very well left to right in an earthquake and provide nice smooth reactions without any significant variations in the structure across the dam left to right. Now we're going to go back to Oroville. There were a lot of different aspects of the Oroville spillway incident that RCC was a great tool, a great material to be used. And I reference the use of RCC in Chapter 8.5 as a foundation replacement. And here, this picture is showing from the original incident the large volumes of flow and the erosion of rock that was going on. And it was clear from the start that erosion of rock and materials would need to be filled in. The foundation for the spillway would have to be filled back in to rebuild the spillway on top of that. And so RCC was a natural material. As a background, this happened in February. This picture was late February in 2017, and the designers knew that once the project started, the rehabilitation started. The spillway would have to be rebuilt and be operational by the following November, just 9 months away. And the work would not be able to start until May. And so really there would only be about 6 or 7 months of construction time. And so the design using RCC made a lot of sense because of the speed and the adaptability of the RCC. And so this picture was probably in August of that year, 2017, and showed how the RCC for that whole area that had been scoured out is being used. And you can see that area clearly here with this wall. This is where the RCC walls start. The RCC was used to fill in these holes and build up a support for the foundation. And this spillway chute is actually RCC, and I'll talk a little bit more about that later. Below the RCC, this is conventional concrete spillway being rebuilt on top of the rock where the rock was fresh. And this was one of the methods we used, that vibrating plate that I showed you earlier for the slopes on the auxiliary spillway, those 1-to-1 slopes, was used on these 4-to-1 slope, this 4-to-1, so it was a flatter slope on the main spillway. And you can see the walls in the background here. So this slide shows the start of that RCC placement down at the very bottom where the spillway accident had scoured all of this rock, and you can see what was left of that rock. And we cleaned it out. We got to a good fresh rock, and we're just starting up. This is one of the first couple lifts of RCC coming up. But you can see how adaptable the RCC is to this varying rock conditions. It's in and out these different slopes of the rock, and the RCC just fits very nicely in here, and the whole idea was to create a nice base foundation for the new spillway. And we use that same plate. So these slopes coming up, this is a 1-to-1 45-degree slope coming up. You can see the markers on the rock for the 30-centimeter lifts of RCC coming up. And we're just moving up and moving the RCC in and around this tremendously challenging foundation of rock, and bringing the RCC material up to rebuild the spillway. And so once we came up out of the eroded hole of the foundation, then we were on the main spillway. And this is early on, probably in June, where we were up to the spillway level, and we're creating a sloped RCC chute to match up with the conventional concrete that was being built further downstream. And then RCC was also being used for these walls, these vertical walls, which was very innovative, I thought. But you can see the adaptability of the RCC in and around the rock foundations, left and right, up and down, coming up and being placed very, very quickly. This is a different angle, a little bit later in the project. The RCC has come up a little bit further, and RCC is being built into the main scour hole from the service spillway. You can see the rock has been nicely cleaned off. The RCC itself is a wide area here, then comes up to a very narrow spillway chute, and you can see the general geometry of these walls as they are coming up along the sides of the slope. A little bit further along the way, the spillway chute is coming up 30 centimeters at a time, and it's coming up to match on top the upper portion of the chute, which was already on solid rock. They are rebuilding that chute and those walls with conventional concrete. So the RCC is rising to meet that concrete spillway. This is that same picture from before, but you can see that vibrating plate being used to smooth the RCC and compact it to get the strength it needs on that 4:1 rough graded slope. This is showing the areas of that had completed the curing. The dark areas to the right are water curing that's still going on. But after a certain amount of time, that curing wasn't needed anymore, and the sandbags were added to take care of the water. And in the background, you can see the wall with the steel baskets that were created being used to create the walls that eventually had shotcrete over the side to create nice walls. So let's move to section chapter 8.6 on cofferdams. RCC is very adaptable and has been used innovatively for river cofferdams. This provides a particular advantage of rapid construction, building a cofferdam structure very quickly when the river flows are low, and the materials are typically already specified for the dam. So if you're building an RCC dam and you need a cofferdam, the RCC can be used for the cofferdam. And the advantage there is it's more stable than a conventional dumped fill cofferdam. It's more impervious, so there's a lot more engineering and control with that type of structure, and it can take overtopping. Um, Large floods can overtop an RCC cofferdam, and then when the floods are over, you can come back, uh, clean out the construction area, and the cofferdam is still intact. So the advantages of the RCC cofferdams are they're strongly stable, they're durable in overtopping events, and they can be built very quickly. The disadvantages are they are more expensive because there's cement involved, and they can be difficult to remove. Sometimes they need blasting even to remove. So it's just a matter of the trade-offs, and in different situations will allow either RCC or other types of cofferdams to be built. But where you need the durability and overtopping protection, RCC is an excellent way to build a cofferdam. And there's in the history, there's been typically two different types of cofferdams, temporary or detached. And this picture shows a detached cofferdam that is upstream of the main dam. And so that's a temporary structure. It can be taken out or even left in place if the design is appropriate. It can be left out there versus an integrated, and there are projects that use the cofferdam as part of the structure itself, and I'll show you how those structures are in a few minutes here. Well, on this structure, this is the Beni Haroun project in Algeria. Um, Thanks to Dragados and Malcolm Dunstan for sharing this case history. This is the integrated cofferdam, where the cofferdam was built first and then the RCC was built over the top of it, almost as a dam raise. But this allowed the materials and the effort that went into building the cofferdam also to be used for the main dam. So this was a really neat and innovative design for using RCC both for a cofferdam and an RCC dam. This shows the project under construction. The structure itself on the right side is actually a cofferdam as part of the structure. And so now it has gotten to the point where they are now placing RCC downstream of that cofferdam and tying it into the cofferdam itself here. In China, they had a very interesting application of RCC for the cofferdam at the Three Gorges Dam. And this picture shows the cofferdam upstream of the dam. And this provided a dry area downstream. And then when they were done, They had gates here, and they flooded the area between the cofferdam and the main dam, and then portions of the dam, of the cofferdam, were removed using explosives. And this was all part of the design, and it worked beautifully and provided good protection for the construction work for several years during the construction of the main dam until the dam itself was ready to function as the cofferdam. So let's move on to raising of concrete dams. Um, Raising existing concrete gravity dams is a specialized application of RCC. It combines RCC buttressing um, and erosion protection and other aspects of RCC to create a composite structure. This composite structure of the existing mass concrete dam and the raised concrete dam using RCC. So it's an economical method of adding storage. It with very minimal or relatively minimal additional costs to an existing dam. Large increments of storage can be added because you're at the top of the storage pool where there's a lot of additional storage available for every meter going up. It minimizes the environmental impacts versus building a new dam. So the owners and the projects typically have already realized most of the environmental impacts of the dam itself, and by raising it, the impacts, environmental impacts, are much less than for building a new dam. So some key design considerations. Starting with the foundation, you're going to have to be excavating and blasting adjacent to existing structures, not only regular structures, but dam structures. And so you want to be sure that the engineering is solid going into that. This picture shown here is from one of my projects that I worked on, where there was some initial blasting going on, and this was a very controlled blasting immediately downstream of the existing dam. The composite structure lends itself to a specialized analysis of the original mass concrete plus the new RCC overlay. And there's structural stresses and thermal stresses that go into that. I'm going to touch on that in a few minutes. And the important thing is to get a good integral connection between the two structures. And so the preparation and the treatment of that interface, where the two structures, the old and the new, connect, is very important. uh, the joints, making coincident joints where there's existing joints in the existing structure, extending those joints through the new RCC so that the new composite structure continues to perform much like the original structure. Matching concrete properties is also a concern. The RCC mix design, the strength, the modulus, these things are important to try to get a concrete for the RCC with characteristics very similar to the original mass concrete. So the structure has minimal amount of changes for it. It tends to, we want it to react in a very predictable manner as it did before the RCC was placed on it. The RCC placement itself needs to be engineered very carefully to maximize for the existing structure. I mean, the existing structure will be a good form for us, but there's also going to be smaller areas adjacent to the existing dam that we're going to have to work around. And so placement of the RCC is going to be very important. And I found that uh, placing RCC for the raised dam is significantly slower than a new RCC dam because the work areas are just not as big, and you can't work with large volumes. So let's do a case study. Let's look at the San Vicente Dam in California, USA, that I was a design engineer on. This was an existing concrete gravity dam uh, near San Diego that was being raised to add additional storage. And in the drawing on the right, you can see uh, what I was meant by there's large amounts of storage that can be added with these incremental raises because you're at the top of the reservoir area here. The connection between the existing dam and the raised dam is important. You want the entire structure to function as a composite structure here. This dam was important because it was an existing water supply reservoir. And you can see in the picture on the left the existing inlet outlet tower to release water for water supply. An important consideration in our design was to keep that tower operational throughout construction so that water could continue to be supplied. Now there was some reservoir drawdown necessary to reduce the stresses on the existing dam and to provide work areas on the upstream areas of the dam. But enough water was maintained in the reservoir to allow the structure and the reservoir to continue to have operations during construction. This was a picture, downstream view of the original dam. You can see that original outlet tower about in the middle of the picture. And then generally the layout of the structure and the reservoir. So this was a water supply reservoir. The existing dam was 67 meters high, completed in 1943. So it, at the time of construction, was about a 60-year-old dam. And it was a conventional concrete gravity dam, about 239,000 cubic meters. So the raised dam, we were raising 35.7 meters to an ultimate height of 102.7 meters using an RCC volume of a little bit less than 500,000 cubic meters. We were adding a new outlet tower and tunnel, and this was part of the consideration because we needed that existing structure to maintain operation during construction, but we wanted to build a new outlet tower, and so that was built separate from the original tower, and then the original tower was decommissioned when the new tower was ready to go. We added a new low-level outlet by built coring a tunnel through the existing dam and to create a large outlet tunnel through the structure. And the spillway was very similar between the new dam and the old dam. And so this overlay shows the original dam kind of looking through uh, the artist concept of the raised dam. And you can see the spillway was about the same size as the original spillway. So step one was to understand the existing dam material properties. So we did some large diameter cores, some 40 centimeter coring through the dam, and we picked up these large samples, and we did some testing at the U.S. Bureau of Reclamation, large testing machine in compression and intention. Um, the idea was to develop a compatible composite structure so that we understood the strength of the material in the existing dam so that we could design an RCC mix that matched that. These 400 millimeter or 40 centimeter cores were taken out of the crest of the existing dam and then sent for testing at the Bureau of Reclamation. One of the key aspects of a dam raise is water tightness. The existing dams will typically have an existing system of seepage control, typically involving water stops and internal form drains. Now for RCC, we want to keep it simple. And so for this project, we eliminated internal drains, we eliminated water stops, and we put the drainage and the impervious barrier on the outside of the dam using a Carpi exposed geomembrane liner. And this provided water tightness for the raised portion of the dam. In the graphic on the upper right, you can see the red part is the upstream liner, and that was only put on the raised portion of the dam. The photograph shows the original dam that has the original concrete, and then the gray color of the Carpi liner is shown just for the raised portion. This drawing or this photo also shows the relationship between the original outlet tower on the left and then the new outlet tower that had multi-levels and also spillway or fish screens that were able to lowered over those openings. And so this was the completed dam. The new low-level outlet was controlled in the middle here by a new gate, which is submerged in this drawing. So the interface is an important, as I mentioned earlier, the interface between the existing concrete and the new RCC. And we know existing dams have a thin layer of weathering, a layer of the concrete that has been exposed to freeze thaw and other weather influences, the solar radiation even. And so it has weakened its material just in a thin layer, a few centimeters or so over the history of the dam. So we want to remove it. For this project, we removed it using high pressure water. And you can see on the far left picture, a machine that's moving up and down and removing that weakened rock and exposing the aggregates of the main concrete dam. So that was first step, was to remove the weather concrete. As RCC is getting ready to be placed, that slope then is cleaned with high pressure water, and grout enriched vibratable RCC, an enrichment of RCC is placed against that slope and vibrated with immersion vibrators. And you can see that here in the middle photo to create a good bond, a strong bond between the original dam, the original concrete of the original dam, and the new RCC. And that helps to create a good strong bond between the existing concrete and the raised dam to create a strong composite structure. An important part of the design is looking at the thermal effects, because we're putting a large amount of concrete on the downstream side of an existing concrete structure, and that new concrete will have a heat of hydration that will impact that joint and impart stresses on the structure and especially that interface. And so we want to look at that as part of our thermal studies in the design phase. And part of that is looking at the RCC placement rate. How fast is the RCC being placed on the downstream side will tell you what that heat gain is and what the incremental loading is on the downstream face of the dam. And another function is the ambient air temperature. The RCC is going to be placed over a period of months, and the ambient air is going to change. And then that's going to impact the peak stress, the peak heat temperatures on the inside of the RCC, which then will impact the stresses. The adiabatic temperature rise of the cement itself inside the RCC, and then these all lead to the RCC placing temperature. So you can control the RCC, some of these stresses, by specifying lower and lower placing temperatures if you don't want the ultimate temperature rise to be too high. And some of the inputs to this analysis include the bottom graph here is the water temperature against the upstream face of the dam. And so you can model that in your thermal analysis. The upper graph on the left is the adiabatic heat rise of the RCC, and that can be done in a testing environment during the design phase. And then the ambient air temperature you can get in this upper right-hand corner through historical data. Hopefully that would be available. And so what that leads us to is a staged construction thermal study. Starting in this graphic on the left, you can see the RCC being placed in these series of lifts to the top of the existing dam and then coming up above the dam. And you can see the thermal aspects of the RCC heating up, and that's that brownish color of the graphic here showing the higher heat, how that gets larger and then gets smaller with time. And then how that heat stays in there for up to about 5 years after construction. It's still dissipating temperature, and it's only after about 10 years that the internal temperature of the dam starts approaching its long-term ambient temperature, which is what you would expect. The photo on the right here shows one of these initial stages of the RCC placement at San Vicente, some of the initial forming, the RCC placement equipment. In the background, you can see the new low-level outlet that was put through the dam through a tunnel that was bored through the dam. In addition to the thermal effects, there's also structural static loading of the dam. And that can be investigated through incremental superpositioning of these loads to the structure. What we're looking for ultimately is what are the stresses at that interface. And so we start on the left here by applying the hydraulic loads and then incrementally adding the RCC loads and watching how the structure behaves. And then we can add um, dam raise as the water loads increase, and we can even add seismic loads as we move up. And eventually, these loads are added all the way to the top of the dam, and that gives you a diagram that's shown here on the lower right, which is the uh, stresses along that interface. This particular graph is the normal stresses along that interface, but you can also get the shear stresses through a good structural analysis program. RCC placement rate has a lot to do with um, the economy of the project, as been mentioned earlier, the stresses, through thermal stresses on the project, um, and the overall constructability. And so understanding what the RCC placement rates are is very important. And it's going to change because you're going to get higher placement rates with the larger areas at the very bottom. And this picture on the left shows near the start of RCC placement. The area is relatively wide, and so the RCC placement it can go much quicker uh, in that area. And so the lower elevations, as shown in this graph, have very high RCC placement rates. But as you start getting up taller and the area gets narrower, toward the top of the dam. And then it opens up a bit at the top of the existing dam when all of a sudden you're going to be very wide again. And so your placing rates get bigger. But as you get near the crest of the dam, where the width of the uh, crest of the dam gets to be less than 9 meters, then the placement rate gets very small. And so it's an important part of engineering that goes into the design to understand what the RCC placement rates are. And so for this case study, this is the completed project. This is the completed San Vicente Dam. There's a brown stain that has been applied to the downstream side to allow it to environmentally match the surrounding areas so that the bright concrete starkness does not stand out. And that was part of the environmental process. And that brown stain fades over time, and eventually the dam blends into the surrounding areas. If that stain wasn't there, you can see the white of the crest of the dam. The entire structure would be that bright. This picture here shows the upstream, that previous picture that I showed, the vertical face of the RCC as it has come up, the new outlet tower, and as the structure has been completed, the new ungated spillway. And I was very, very proud to be part of this project and construction. I have one more case study for you as I'm getting close to wrapping up the presentation. And this is just a very brief project that's in the design phase right now. This is the Gross Dam in Colorado. And the interesting part about this is similar to San Vicente in that the original dam is a concrete gravity dam. But as you can see from this photo, the dam itself has a curve, it's curved in plan. And so in our design, we wanted to take advantage of that curve to save on material. And we developed an approach to change and transition this concrete gravity dam into a thick arch dam. And what that allowed us to do on this picture on the right, the gray cross section shows a typical gravity dam with the existing slope of for the existing dam of 0.662 horizontal to 1 vertical. So that if we were going to raise it strictly as a gravity dam, that would be the flatter slope of the downstream face. But by going to a thick arch and taking advantage of the arching action of the dam, we are actually able to steepen the downstream side from 0.662 to 1 to 0.5 to 1. So this allowed us to save all of this material between the red line and the outside blue line. And so you can see the amount of RCC that is not necessary and can be saved. So that creates a significant cost savings for the project and for construction. And the picture on the left shows that the center red portion of the dam is the main portion of that thick arch. That's the steeper slope. And then we had tangential thrust blocks. We designed this as an arch dam, which these thrust blocks are tangential to the curvature of the dam and plan, and that takes the thrust of the arch and brings it to the abutments on either side. And the main spillway that was in the original dam as in the middle was kept nearly the same geometry in the raised dam, a very similar approach to what we had at San Vicente. So just some simple graphics of the project. This was the picture of the original dam, and you can tell that we don't have the abutments here. And so that's why those new tangential thrust blocks were added. The arching action works very well in the lower valley, but where the valley goes away and flattens out, we needed to add those thrust blocks that were shown in the previous slide. And so then the raised dam would look like this. Again, this is still in design. Construction has not started yet, but this is the artist rendering of what basically the structure will look like with the main dam, the thick arch in the middle with the ungated spillway, and then these thrust blocks on the left and the right abutments that bring the structural loads to the left and the right on either side of the structure. So the last chapter, the last section of chapter 8 in Bulletin 177 is other uses, and this is just a catch-all of different aspects of RCC, and it's really just meant to say that there are many other innovative applications of RCC that are possible through the creative mind of engineers continuing to find new opportunities in the technology. And I've showed you some of those in this presentation. And I have two more to show you. And these both come from the example, the case study of Oroville Dam. And Oroville provided the opportunities to do some of this innovation because it was an emergency. It was a had some very strict schedule constraints on it, and we used the RCC to the best extent that we could. And one of the things we needed in the spillway was we needed to have vertical walls for the spillway on a sloping surface that was sloping up the hill. And so we developed this innovative use of using hill thicker wall baskets, like a reinforced earth type approach, but for concrete. And these baskets allowed us to form vertical faces um, as we went through here. And we had these outside slopes, this 1-to-1 45-degree slope on the outside. And that was typical of that hole we were filling uh, that was eroded by the original accident. And then that was coming up. And then as we got to the chute surface, we formed this rectangular cross section for the spillway chute. And we would eventually come back and add uh, uh, a high strength layer of RCC over the top of the base layer of RCC. So I want to show you some pictures of that as it was going through being developed. Uh, this picture shows you the base of the RCC, very wide as we're going up, but that 1-to-1 slope on the outside, that you can see that slope that, on the closest side, that's that outside wall coming up. And then the wall itself ended up with about a 5-meter wide uh, top of that wall and about 5-meter high wall itself. And so we had this wall coming up and building it. So it had a bit of a orthogonal shape here as we were coming up, but then the top of it was rectangular as we were going. And this picture also shows some of the work that was being done. The scaffolding has been added by the shotcrete contractor to allow its workers to get in and to spray shotcrete on that inside of the wall and smooth it as we were going up. And so you can see the amount of materials. This is a good example of the benefits of RCC. Not a lot of equipment on the surface, not a lot of workers, but the RCC is going in very, very quickly. This is those walls I was mentioning. The left picture shows the outside of the baskets. Some reinforcing was added there and dowels to strengthen that. And then the shotcrete was applied and smooth, and you can see what a very nice smooth surface we have here. Um, it was designed so that when the spillway was finished in November of that first year, that if necessary, water could be put down at a high velocity down this spillway with a high strength RCC overlay on the chute, and then these shotcrete walls. So I mentioned the overlay. The RCC, as we were coming up, we were smoothing it with that vibrating plate and creating a rough grade on 4-to-1 coming up. We came back and some of the material was a little bit loose, and so you can see some of it was carved out of here. And then we put a higher strength RCC, and we did a mixed design that added strength, that developed its strength over a period of 28 days. Got up to its design strength, but it was placed like RCC. This is a 4-to-1 slope. Um, we couldn't get dump trucks onto the surface, so the RCC was dumped above the walls and was transferred using backhoes onto these special dump trucks that had track-mounted rigs on the spillway chute. They were moved around on the spillway chute and then were dumped. And so this then usual RCC placement using rollers and dozers um, and were added here, and then the RCC was placed, and then the smoothing was done by that same plate, that same vibrating plate that we used for the 45 degrees was used like a trowel to smoothly finish the RCC and give us the compaction we needed and a nice smooth surface. And you can see the finished surface here to the right with some of the dowels sticking up. The shotcrete walls on the outside, very nice. That it has a curing compound that gives it a white look to it, but turned out to be very nice as a spillway chute. And this is the completed spillway chute that was at the end of October in 2017. Once the upper portions of the conventional concrete and the lower portions of the conventional concrete were done, the RCC was finished at the same time, and the spillway was available for discharges if there was another flood during that year. And so RCC, this is all RCC here, the spillway chute itself and the walls. I thought a very good application of RCC, and this was all done in less than 6 months of RCC placement. So I was very excited about that. And so I hope that with all of these different case studies and these different applications in this chapter of Bulletin 177, that I've been able to give you an overview of the many advantages of RCC and other applications other than just building a dam. And so there's these good applications that are out there, and as engineers, you should challenge yourself um, for these type of applications. And I'll leave you with the statement from the Bulletin 177 that the use of RCC for the rehabilitation of existing structures and construction of new concrete dams, including dam raises, continues to expand as we, as engineers, as we utilize the many efficiencies of this material and the placement methodologies to benefit project economy and schedule. So I encourage you to be creative. The other aspects of RCC that are presented in the other sessions and the other parts of Bulletin 177 give you all the basic building blocks of RCC material designs and constructability. And this chapter, I think, shows some of the different rehabilitation and dam raise applications of RCC, and they work. I have worked on them, and it has an amazing material, and I encourage you in the projects that you have there in India. I know there's going to be many uses for this very important material and placement method. So RCC is an amazing aspect for us, amazing tool for us as dam engineers. And so I encourage you to continue to use this material, but always keep in mind the safety of our workers during construction and the safety of the dam during design and during construction and during operation. Dam safety, as we know, is a paramount and a vital aspect of what we do, and it should be in what we think about every day to make our dams safe, to protect the structures and the people that they serve, especially the people that live downstream that look to us as engineers to keep them safe. So with that, I'll say thank you very much for the opportunity to make this presentation. And I think that I will be have the opportunity to answer some questions either directly or remotely. So thank you very much. And I will say goodbye.
Thank you. Thank you, sir,
Thank
for
you.
making an
Thank you, sir, for
excellent and
making an
detailed
excellent and
presentation
detailed presentation
on RCC dam rehabilitation and raising inclusive of the case studies. May we proceed further for the question answer session? May I request to the participants for their questions, please? Yeah, Mr. Anil Jain, would you like to ask?
Yeah. Thank you, Rajat sir, for your nice presentation. Earlier also, I had an opportunity to listen to you on Oriville Dam. So I have some question on that itself. I noticed there were large scour holes on eroded rocks. So did you fill all those holes with the RCC? Because there must be some equipment constraint itself. Wherever it was not possible, how you managed it? Did you go for the CVC or something else? Second question is that you use it for RCC in a splash pad also. So what kind of velocity you were expecting there, and your opinion, what kind of velocity it can sustain against erosion and RCC if you go for and what was the proportion of the cementitious material which you use for the splash pad and those things? And okay, first you reply, then there is one more question, but that is different.
Well, thank you very much for your questions. Let me start with in the main spillway that had large scour holes. Yes, some of those holes were filled with CVC. The smaller ones that were very tight, and we were able to fill those during an off shift. Those are primarily in the bottom, and then cover them with RCC very quickly within 24 hours, typically. And so we, in some cases, use some quick setting conventional concrete so that we were able to adjust the foundations there. So it was that's a very good question. As far as the splash pad, it's been a while since I've looked at those the design details, but I seem to remember that the velocity that we had was about 15 to 20 meters per second on the flatter parts of the splash pad and in the main spillway. I'd have to go back and look at it. And as far as the mixed designs, I don't recall offhand, but I will find that information and get it back to the organizer so they can publish it.
Yeah. Okay. One more question. In the splash pad, you used steps. So in general, this is just general question, because what kind of ratio you use between the riser and the tread? It must be quite. There must be about 5 or 6.
Yeah, it varied. When we were trying to keep 2 30-centimeter steps, and then we were adjusting it for the steps as we were going, and we were trying to keep a normal thickness of about 3 meters of concrete over the slope. So as the slope was going, the normal thickness of the RCC was about 3 meters, and so we adjusted the rise and the run. We adjusted the run of the rise was fixed of the RCC to adjust that, and it varied, as you said, based on where the slope was, and then as we got closer to the up at the top, it flattened out a bit.
And you used rebarring to connect it the existing weir to the splash pad. So did this rebarring rebars, they interfere with the compaction process of the RCC? And
No, that's a good question. We first did a high pressure water on the original concrete to remove some of the looser materials and get a clean surface. We also used GEVR against the surface, but to have that positive connection and working with the regulatory agencies, they really wanted that rebar connection. So we drilled into the existing dam and epoxy grouted that, and then set the rebar on the RCC with a plate, and then we compacted the RCC around that, and then we did that as we went up, and so we did not have any problems with the compaction process with the rebar in the RCC. It worked out very well. It was similar to what we use for forms, tiebacks for forms with a plate on it. Very similar to that in the RCC.
Okay. And in one of the project, you mentioned that you used RCC at the downstream of the dam in energy dissipation section to protect the spillway against erosions, both on left side and right side. I'm just missing the name of the dam. It was probably uh, was it Olive Hand Dam?
On the left side and the right side for
You
erosion
used
protection.
RCC for the
No,
left
it was.
and right bank.
If it might have been Platter Navasi that had
So-
it on
so-
in the chute
I-
in the
So
channel.
my question is that it must have been height must have been say 20, 30 meters or maybe more. So did you manage it in a constant slope or you did stepping also there, and means was some reinforcement was also used to maintain that height?
I'm not familiar with the design details. That was not, from what I saw, that was not stepped. It was probably a formed surface, but perhaps one of my colleagues would know from the different shoots. So what I've seen um, uh, at the different projects I've been involved in, we've used forms for those areas. But typically it has not included reinforcement.
Okay. Last general questions. Uh, in your opinion, what would you suggest? Should we use a membrane as a upstream phase for as a water barrier, or we should go for conventional our water stops and foam drain types, because they must be interfering with the pace of the construction? So, what is your opinion? What is your take on that?
I think there's different opinions on that. I think that the 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 best for the dam, for dam engineering, is to have a good conventional concrete design that doesn't need that membrane on there. I think if you can work the situation with the dam that it does not need a membrane, I think that's the purest way of doing it. But the situations are different. Where we used it in California, it was a high seismic zone, and there was a lot of movement in the dam, and we were afraid of cracking. And that membrane, because that carpi membrane, it expands about 600%. It allowed us to have confidence in under high seismic conditions that the upstream face would remain watertight. And for that project, it worked out very well because it allowed us to go very, very fast with RCC placement. A Livenheim Dam is one of the fastest built RCC dams in the world, and it was like that because we simplified the placement of RCC. In my opinion, that the membranes were the key to success for that project as far as going very quickly and having a nice solid watertight barrier. And it still remains one of the driest RCC projects with as far as leakage. And so I think it depends on the different conditions and different design situations in the dam. And so I think the engineers have to create a judgment. I have a dam raise with a membrane on it, and I have a dam raise that does not have a membrane on it.
Okay.
So I have done both.
Thank you very much.
My pleasure. Thank you very much for your questions.
We have next question from Mr. Ashwani Verma.
Yes, sir. So I wanted to ask one question. Like if we have a situation wherein there's a damaged spilling basin and and then we are trying to rehabilitate using RCC. How do we cater to the uplift forces? I mean, what arrangements can be done?
I think you need to look at the uplift, creating the drainage relief underneath the to relieve that uplift, same as you would for any other conventional concrete surface. The important design as you put RCC to rehabilitate existing stilling basins is to make that good connection, to make sure that you remove all of the damaged concrete and you get a good connection and a good geometry. I don't think that you need to provide drainage between the old concrete and the new concrete. I think if you design and have good construction quality control and you get a good bonding between those two concretes, then you don't have to provide drainage in that area. And so then it's just the subterranean drainage, the uplift underneath the whole structure, and that should have been part of the original construction. And if it's not, I think through engineering you can provide that in a rehabilitation effort. But that's a very important aspect so that you don't have future problems.
So does it impede our speed of construction?
I don't think so. I think that the whatever drainage it was there in the original dam needs to be considered in the rehabilitation engineering part of it. And I think the RCC the speed is going to be slower because it's a smaller confined area in the stilling basin. But I and you'll have to look whether it makes sense to use RCC or conventional concrete. If the RCC is best when there's large open areas. When it was used at Tarbela, there was a big hole, a big scouring, and there was a lot of concrete had to be placed very quickly. The same thing for Oroville. We needed to place RCC very quickly in a large area. But there's a lot of stilling basin repairs that are better used for conventional concrete.
Nice. So another thing, like we were talking about vertical walls. So can we use those reinforced mats, those baskets you were talking about, regularly while we are creating a spillway right in the middle of the RCC dam?
So the baskets worked well for what we were trying to do on the inclined slope. I would be careful using those on a conventional concrete on our gravity dams, our RCC dams for spillway walls. I don't think that they would be appropriate for those type of walls, and you would be better served with either a conventional concrete training walls that are tied into it, or somehow working your forms for the RCC as far as having an indented spillway. And there are many examples in the ICOLD RCC database that you can look for the different dams that have spillways. And I'm sure that there are many examples of different ideas on that. I think the subsequent presentation from Mr. Rafael Ibanez, who is a contractor for Dragados. That would be a good question for him because he has seen several of these.
Okay. And so while we were talking about that valve house, the foundation of a valve house, we talked about unformed RCC. So how good it is for erosion, I mean against erosion, that unformed RCC?
Yep, no, that's a good question. And that was at Portuguese Dam, and Mr. Ibanez would be a good person to ask about the details. But I think it works very well, and so you'll get compaction to a point, and then the RCC will fall off, and it creates a rough surface. But you still have good compaction on the inside, and so that will create a strong concrete. So you'll lose a little bit, but I think in my opinion, it provides, you can still get a good resistance to erosion with unformed RCC, as long as you understand that there'll be a certain amount of material on the outside that doesn't have the fully compacted strength.
So can it be possible that the erosion progresses inwards where we have compacted it well?
I think if you have good compaction, the erosion will not continue inward, but it depends on the geometry of what you're looking at in a shearing of like a flowing of water along that RCC. I don't think that I think the RCC is robust enough that it will resist that.
Thank you, sir. And just another small question. We were talking about using RCC for slope stability on downstream of a dam on the downstream side. So, what would be the minimum width of an RCC wall for it to be economical?
Boy, that's a good question. The minimum width of RCC is usually set by the equipment that you use to roll it and build it. And so I would think that the usually and I get uh, there's been different applications of it, but I would say um, 4 or 5 meters thickness for the equipment to get a good compaction would be probably a minimum width in my opinion.
So that should be like 4 to 5 meters at the top. I mean, the base should be larger.
The base would be larger. That would be the minimum thickness.
Thank you so much, sir. It was a pleasure.
Thank you for your question.
Thank you, sir.
Thank you, participants, for such an interactive question answer session. I guess there is one more question from Mr. Arun Pratap Singh.
Sir, how do you provide contracts?
I'm sorry, how do I provide
Which we generally provide in RCC?
the contraction joints?
Yeah, contraction joint, and what is
Yeah.
the spacing of contraction?
So for the RCC projects that I've been involved in, we have provided contraction joints using steel plates that were vibrated into the RCC. They were about 2 to 3 meters long, and they were the height of about 30 centimeters, and they had a little hook on the bottom, and they were vibrated into place and left into place. And so at Olivenhain and San Vicente and at Oroville, we used the steel plates to create the contraction joints in the dam.
Yes, regarding spacing.
The spacing is going to be driven by your thermal analysis. So you can look at your thermal analysis to drive that. It will be different for different materials. For raising existing dams, we keep the same spacing as was in the original dam. For a Olivenhain Dam, which was a new RCC dam, our spacing was I think it was probably 50 feet. I think it was the there. So what's that about 18 meters?
Okay, sir. Thank you.
You're welcome. Thanks for the question.
If the participants still have any further questions, they may write to us. The organizer will be
Ma'am, I have one question more.
Yeah, please.
Sir, I have question. What are the non-restricted test method to follow the ensure the quality control during the construction of the RCC?
Oh, that's a good question. So
Non-restricted test method to follow during the construction.
So that's a very large question about quality control during construction. The RCC Bulletin 177 has a chapter on quality control that was.
You follow.
I'm sorry?
During construction, you should follow.
Yes. So good quality control starts with the design and putting together good specifications for quality control. And there are different aspects of the quality control, but it starts with the material supplies and then the validation of the materials as you're forming RCC. The main quality control on the RCC lift surface is the VB test that tests the consistency of the RCC as it's coming out of the plant and in the on the lift surface, so that you are routinely checking the consistency, and that will validate the amount of water and cementitious materials, or the workability of the RCC, and also the nuclear density gauges that we're testing compaction. But really, when you're out on the RCC, I found the best quality control is the engineer walking and having an experienced engineer with RCC and watching how the RCC is being placed and then walking on it and the way the RCC feels as you walk on it. I think Dr. Dunstan has described it as a firm jelly or something like that. It's a look and a feel that working with RCC over several projects, you get a good eye for. And I don't think there's anything better than an experienced RCC engineer out on the lift surface to watch the quality control. But there are many aspects that are by specification, and there will be a presentation specifically on quality control later on in this training. Thank you for your question.
Sir, similarly, we have also a query in mind. What happens during the after construction of the project dam, after 10 or 15 years, any treatment required in the dam? What we should follow, like the conventional concrete or other any method for the RCC?
I think once the RCC is placed, the typical monitoring and instrumentation that you have for concrete dams is appropriate for RCC. What you'll see different for RCC are thermal thermistors in the dam that measure the temperatures. And you should have, for RCC design, have a good design that has a model for how hot the material is going to get and then cool off. And with that model, you have thermistors installed during construction that measure that. And so for periods of 5 to 10 or 15 years after construction, you can still collect data on the thermal performance of the dam and match that to what the predictions were. And I think that's the longest term instrumentation for RCC specific, but you'll definitely have, survey instruments, movements, and then of course your cylinders that you've taken during construction and testing those at periodic times.
Sir, if any happened due to the earthquake or shrinkage cracks or any other cracks or any erosion due to the overtopping, then what can we do? Treatment.
There's different solutions for different problems. With cracking, grouting is an option. Doing at Upper Stillwater in the United States, they did some grouting of the cracks in the dam, and at some other projects, there was an upstream membrane liner was used when there was a lot of leakage through the dam. At Olivenheim, we had an unexpected crack form, and we ended up using a piece of the exposed geomembrane liner to cover that during construction, and then it sealed it up very well. And so there's different options depending on what the situation is. But it comes back to good engineering and good sound judgment.
Okay, thank you, sir.
Thank you for your
Thank
questions.
Thank you all. For any further question, I would request to all the participants, they may write to us, the organizers, CBIP. We will get back to you over the email after getting your answers from the speaker. Here, I would like to convey my special thanks to Mr. Michael Roger for sparing his valuable time for conducting today's virtual session. He is very kind enough to make himself available at the odd hours for this session, which shows the dedication, commitment, and keenness to share his experience with the Indian dam professionals. Thank you, sir. I'm sure all the participants must have benefited from his vast knowledge shared during the program. Thank you very much.
Oh,
See you all.
yes, you all have been very kind, and thank you very much. I apologize, but I thank you very much for all of your kind words. You all are very, very good people. Thank you very much to ICOL Vice President Devendra Sharma for his kind words at the beginning. I'm humbled to be here and very humbled to be with the Concrete Committee. That is with Dr. Dunstan and Dr. Quentin Shaw and many others that have been worked so hard on this RCC bulletin. I encourage all of you to get a good copy of it. You can download it for free from the iCold website, and a lot of hard work from a lot of smart people went into it. I was fortunate to help them out and be part of that. So thank you very much. It's been an honor to be here with you, even virtually, and thank you very much.
Thank you very much, sir. Thank you.
Okay.
See you all after the lunch break at 1500 hours IST.